Right, so welcome to the last session. First talk is by Rohan Goge. He's a PhD student at University of Michigan, and he'll talk about non-adaptive stochastic score facilitation.
Can you hear me? All good? Cool. Thanks for coming to this talk. I know it's been a long day and it's been a long 2 days. Let me just start with the problem. So we're going to be interested in this simple application. So say we have a complex system which is made of many components, and these components fail with like a known probability, and our goal is to test these components to give a risk class to the system. So for example, let's say we are counting failures, and we have these three risk classes that kind of depend on how many components failed in total. Okay. So the way you would kind of solve this problem is you will start testing, and you'll keep track of the total number of components that have failed so far and the total number of components that could fail as you progress. So for example, let's say the first component you test is working. So now we know that the total number of components that could fail is 8. And you would keep testing and like kind of note that once you reach this point, where the total number of failures fall basically in the same class, you can kind of give it a risk class and you can stop testing. Okay. And that's our goal. The goal is to test certain components to quickly give a kind of risk class to the system, and then you can go and do preventative measures or whatever operationally. Okay. This is the main motivation for this problem. And if there are any questions, feel free to stop me and ask. Is this clear? No? Okay, cool. So the stochastic score classification problem basically captures this setting where we are given some items x1 to xn, where we have to pay a cost ci to probe item xi. On probing, it could work or it could fail, and we know the probability with which it fails. More generally, we could have a weight for each item, which kind of tells you how important that item is. We have a score function R that gives a score to the whole system, and we have kind of cutoff values that we can use to give a class to that system, right? So, for example, class J corresponds to kind of cutoff to like scores being in this range, which is kind of given by like the cutoff values that we get as input. Okay. Any questions about the problem? Okay. So going back to the sequential testing application, we can think of each component as a single item, and we can think of the weights as one. We have three classes where we have cutoff values as 2 and 7. That's how you kind of model this special example in the stochastic score classification framework. Okay. So what do solutions look like for these kind of stochastic optimization problems? One class of solutions are fully adaptive solutions where you make a decision, you see the outcome, and kind of based on this kind of outcome, you make future decisions, right? Second class of solution is kind of non-adaptive, where you would fix a query order up front and you would probe items from this fixed query order till you reach a stopping criteria, which is that you can say with certainty that your class is like J or something. Yeah. So these are like the two kind of solution concepts we'll become interested in. A challenge is that fully adaptive solutions can be like thought of as stochastic DPs. And these are kind of really big size DPs. So like if each kind of random variable has two outcomes, these have these would have these would have a really large state space. Sorry. And even trying to come up with good kind of non-adaptive solutions is going to be hard for this problem. One thing though that's not known is that if you were to look at the problem where you have like weights equal to 1, we don't know if that's NP hard or not. So there you could kind of try to come up with fully optimal algorithms, but for a general problem, it's known to be NP hard, right? which means that we can't come up with algorithms that simultaneously have these three properties. That is, they have a fast runtime, they work for all instances, and they give us the true optimal solution. So the way we deal with this is we try to come up with solutions that we can quantify, have a good guarantee when compared to the true optimal solution. And the challenge here also is the fact that the fully adaptive solution that's optimal is something we can't write down as well, right? So we want to also try and compare to these solutions that we can't write down. Because of these, there has been limited work on this problem. So a special case that's been studied nearly 6 decades ago is this problem that you want to test a single component has failed or not. And for that, we have a non-adaptive algorithm that is kind of greedy, which is built on CI over PI values, and that gives us the kind of best solution. A special case where b is equal to 2 has also been studied, where you can think of it as kind of stochastic function evaluation on a linear threshold function. For this, we know a 3 approximation algorithm, which is fully adaptive. Okay. For the general stochastic score classification, we know 3 algorithms. The first one is O of log A approximation. This kind of uses the stochastic submodular curve approximations, and it's going to be fully adaptive as well. We can also use this 3 approximation algorithm for each of the thresholds that we have for the B classes, which gives us a 3B minus 1 approximation. These 2 are fully adaptive. And for the special case, again, where kind of weights are 1, we have a 2B minus 1 approximation, which is not going to be, which is non-adaptive. So from this, the major kind of open question is that can we design a non-adaptive algorithm for the stochastic score classification problem? Okay. Any questions? Yeah. Right. So expected class. So we want to know for certain. So there is a true realization that we don't know, and we want to start testing till we can figure out what was the true class in some sense. Yeah, that's right. Any more questions? Okay. Right. So the main result is that we show we can get non-adaptive algorithm, and it's a constant factor approximation for the stochastic score classification problem. And since this is compared to the fully adaptive algorithm, we also give a constant factor gap for this problem, which is the ratio of the best non-adaptive solution to the best fully adaptive solution. Okay. Any possible? Yes. So you're given kind of class B. Yeah, that's true for any input, any plus whatever number of classes. Yes. Right. And another feature that 3 more features that we give is that we give a list for probing that stays the same, and it's kind of not dependent on your kind of cutoff values. So if you have a fixed set of items with a fixed set of weights, we give a list based on that, and it does not change if you change number of classes, if you change the kind of cutoffs or anything. Secondly, we use a kind of greedy rule to kind of give this list, so it's really fast to compute, and we can handle kind of negative weights as well. So any questions about the framework, the results, kind of solutions that we're looking at? Exactly. Yeah. Yeah. So basically what we're looking at is, let me just go back. We're basically looking at a list of this form where I'm going to tell you you should be probing in this order. You can't skip. You just have to keep probing in that order till you can determine a class. And the cost of that solution will be compared to a fully adaptive solution. That's kind of constant factor. In expectation. Yes, that's right. In expectation. Oops. Okay. Any more questions? Cool. So So the kind of key idea for our technique is the following. So suppose you have probed a subset of elements already, and we know this score. So this tells me the score of the stuff I've probed so far. And if I look at this term, it tells me the score I've lost. So this kind of tells me that those items which was zero, they kind of they give me an upper bound on the score that can happen. So you can kind of think back to a number of failures example, where if something was working, we know max number of failures has to go down by one. So that's a kind of similar idea when we have kind of general weights on these items. Now, if you happen to be in this situation, this tells you in some sense that you're in your true class could be in two different buckets, right? So we can't stop probing at this point. So we must keep probing and come so much a fully adaptive solution. So if you're at this point, you can't do anything but to kind of keep probing till you fall in the same class. But if you are in a situation like this where your two bounds fall in the same class, then you can stop probing. Okay, that's kind of the main intuition, and we're going to try to capture this intuition with our algorithm. Okay. Okay. So to capture that, we define two terms, R0, R1. So these two rewards basically are used to give upper and they used to give upper and lower bounds on the total score. And if I'm using this rewards, we'll give like a list of predetermined. We'll give a predetermined list for probing. Okay. So how do we fix this predetermined list? So basically, what we'll do is we'll build kind of two lists for each of the rewards, and the goal will be that the list for reward 0 seeks to maximize that reward, basically, right? So we are kind of going to build these two lists where list L0 seeks to maximize reward R0. Okay. These two lists are built in phases, where in phase I we get a budget come to raise to I, and then kind of once we build these two lists, we'll kind of interleave them to create a single list, and that's going to be the final list. Okay. So now, how do we build a single list? So let's kind of fix some B, and we'll see how to build a list L0 or L1, whatever. Okay. Right. So say you fix the phase I, and now you want to maximize a reward for the list that you're building, given come to raise to I like budget for that phase. And the way we'll do that is we'll use some knapsack algorithm. So we'll just say expected rewards, and we'll try to maximize that reward with respect to the fact that we have a 2 raised to I budget. Okay, that's not it, because in certain cases that's not going to be enough. So I'm take for example this case where we've probed some elements so far, and we have like scores. Let's say we have come in score 3, we max score 6, and we have 2 items remaining, right? So now if I look at expected reward, this guy's 1.2, this guy's 0.99, right? So you would want to select maybe this guy, but can you see that that's not like a good solution, right? Because this is going to give you 1 with 0.99 probability. So you'd rather select this, quickly go into the same bucket and stop probing. Is that clear? Right? Okay. So this is a better choice in this setting. But a different setting is as follows, where our score is 1, and now maybe this is the better choice to probe. Okay. So we need to kind of deal with the situation that depending on different kind of realizations that we've seen so far, there may be different items that are suited to probing. Okay. And the way we deal with this is we use kind of truncated rewards. So we'll truncate each reward by a certain scale, and we'll use that to compute the reward, and then we'll try to maximize that, right? So for example, in the previous setting, if we look at two truncations at like scale 2 and scale 3, we see that this X2 item is kind of better at scale 3, where scale 3 gives us 0.33 reward and scale 3 gives us 0.4, right? So the main key idea is the fact that at different situations, we have different items which are like better. Okay? And we want to try and capture this. So if we include all items for each scale, we'll suffer like a max loss in kind of approximation ratio. We could use standard doubling tricks and make that kind of log a max, but we can't get rid of that loss basically if we use this naive approach to take every single scale. Okay. The fix for this is to identify a critical scale, where a kind of critical scale is one where we show that you can get high reward, where we can get high reward at that scale, and any optimal algorithm outside of the stuff we select cannot get a very high reward. So it's enough to just pick one scale. That's how we don't suffer this kind of log a max like loss. Okay. Any questions? So so this is the whole algorithm basically. So we're gonna build each list in phases, where in each phase we'll try to figure out the critical scale, which is a simple condition, and then we'll include all items with good expected reward for that scale with a budget with a fixed budget. We'll create one list and we'll have two lists for the two rewards, and that's it. Okay. That's the whole algorithm. Cool. So if there are no questions, let me talk a bit about the proof. So we need some notation. So let's kind of set that up. So we have opt and alg, where they denote the cost of the fully adaptive optimal solution and the cost of our solution. And the theorem boils down to saying the statement that expected cost of our solution is a kind of constant factor of opt. Okay. We will kind of define two more terms. The first one being O of I, which is the probability that a fully adaptive optimal solution pays cost 2 raised to I. With this, we can write down an expression for expected opt. Oh, sorry. Yeah. And second term we define is A of I, which is the probability that we pay greater than alpha times 2 to the I, with which we also can write down a simple expression for our cost. And now note that if we can compare these two terms, then we have a way to compare the two terms that we care about, right? And that's basically our key lemma. That's to show that indeed we can come up with a comparison to relate these two probabilities. Okay. And with this, we can show the main lemma. With this, we can show the main theorem. Where note this alpha is a kind of constant factor that shows up here, and here. Okay. So now the proof boils down to just showing this key lemma. Okay. Okay. So we want to show the key lemma, and to show this, we'll condition on the first few phases. So we'll kind of say that sigma is outcome of the phases up till I. And with that, we'll define two more terms, right? So this is basically the same term conditioned on sigma, right? So OI sigma is just saying the probability that opt costs more than 2 to the I conditioned on sigma. And the same way we define A of I comma sigma as well. Okay. And now I claim that it suffices to show this statement. And we'll see why. So first, first, if we condition on sigma, note that AI minus 1 becomes fixed, right? You either finished or you've not finished. So it's going to be either kind of 0 or 1. If it's 0, then that means we finished in phase I minus 1, which means we finished in phase I, right? So this would hold trivially. If it's not, then it's 1, and then we get the statement, right? So if we can show the statement, then we can show, then we have like the statement holds for all sigma, which means it would hold in general as well. Any questions? Right. So now we are basically trying to show the statement. And to show that, we again define two more terms, which is ops reward and our reward. And with that, one assumption we'll make for now is that the probability that opt gets more reward in phase I than us, conditioned on sigma, is small. It's kind of like 0.15, let's say. Okay. And this is kind of all we need to like finish off the proof. So suppose opt finishes in phase I, which means that it costs less than 2 to the I. That means that there was some class J that made it stop. Okay. Which means that this condition is true, that the probability it finishes in phase I, which can be written as this term, is the probability that there is some class J such that it fell into the class J, right? So you can think of UB and LB of J as follows. So you can think of it as like it reached, some score such that it was greater than the minimum for that class, and it fell into the score such that it was like it had a good upper bound on that class as well. Okay. Right. So if opt stopped, then we use the fact that we get better score than opt with high probability. Basically, so we'll show that the probability that we did not get better score is small, right? So we have a kind of we show so with kind of high probability we get better score, so we must have stopped. That's it. And kind of using these two points, we can finish off the proof of the statement from before. Okay, so it's a pretty simple proof. And the key idea here is that we only have to take a union bound over two things rather than taking them over like B classes. If we had to take it over B classes, we would have to suffer a loss B again, like the previous paper, which we don't have to. And to show this assumption, we basically need to use kind of critical scale to show that, when we pick according to the critical scale, there is, with high probability, we get a certain reward. And again, with high probability, a fully optimal algorithm cannot get more reward than us if it didn't select the stuff we selected. Okay. So I'll stop here with the technical part. I'm happy to talk about this offline if there are any questions. But let me talk about a couple of extensions from this problem. So the first one is a kind of batch setting, where actually I can take questions over here if there are any questions. It's a good point to take questions if anything was confusing. Okay. Yeah. What? Right. Okay, so I said the scale is used to prove this guy, basically. So with the scale, you'll just say that the probability that we get high reward. So the scale tells you that okay, I get that with a high probability we get some reward kappa, let's say, and if opt was not given the selection that we made, it can't get reward greater than kappa, which basically will say that the flip probability is like high, at least 0.85. Yeah, so the scale, I didn't define it fully. I just, let me quickly go back. Yeah. So basically, the scale is basically kind of one scaling such that, we get high reward when we pick according to that scale. And if a fully optimal algorithm is not given the solution that we took, it can't get a very high reward, right? So So if you look back to the example, basically a scale is just saying that, hey, I'm going to scale each reward that you get by a certain number, and then we're going to use that to compute expected rewards. Because just choosing rewards is not good, since there are some situations where you could have high expected reward, but it's not very helpful, right? So if you look at the first example that I gave, so in this situation, this guy has a high reward, right? And that's not very helpful because this is a better choice in expectation. Cool. Any more questions? Okay. So the first extension we consider is kind of batch setting, where now we can run tests in a fixed batch, right? So suppose we want to test set S. Now we have to pay two kinds of cost. First, we'll pay a setup cost F, and then we'll pay a cost of testing, which is kind of summation over CI. Okay. And for this setting also, we show the same result. We have non-adaptive algorithm, but you get kind of constant factor. Okay. Second setting is trying to capture a complex system that performs D number of tasks. So now each item has a d-dimensional kind of vector for the weight. The score is kind of d-dimensional. You have cutoffs for each dimension. And the goal now is to give a risk class simultaneously for each dimension with a low testing cost. And for this, we have a non-adaptive solution that gives a d square log d approximation. Any questions? Cool. So let me talk about computations now, since I have 3 minutes remaining. So I'll go through computations quickly. So we create synthetic data as follows. So we set some n. We choose pi randomly comes 0, 1. We set cost uniformly at random, and we test over many samples and instances. We test them on a few different benchmarks. So we test over the 3 adaptive algorithm. We test over the non-adaptive 2b minus 1 approximation, kind of random query order, and lower bound. Let me talk briefly about this kind of lower bound. So suppose you know the true realizations and you just want to pick a set of items to certify the class of that. Suppose you know that, hey, the class of the system is J, and now our goal is to just choose the min cost set which certifies this fact. Okay. So we can write the following integer program to capture that. And if we average this over all realizations, we get a kind of lower bound for this. Okay. And it's not known actually if there is some integer program that captures the like stochastic score classification problem either. Okay. So let me talk about the first set of experiments on the stochastic function evaluation problem with 2 classes. So for this, we get the following result. Okay. So we are pretty close to the fully adaptive algorithm, and also pretty close to the information theoretic lower bound. Okay. And in terms of our runtime, because it's fully adaptive, it's like much worse than us. So as we have more number of variables, we pretty much stay within kind of 0 seconds, while this is just increasing. Okay. Questions? For the general stochastic score classification problem, we test with 2 different settings. So we test with b equal to 10 and b equal to 15. So for b equal to 10, we get the following result. We are outperforming in cost the 2b minus 1 approximation algorithm. And we see the same thing for the kind of b equal to 15 setup. We do better than the 2b minus 1 approx. Any questions? Yeah. So we are just comparing the cost of testing, right? Yeah. Cool. So in a kind of different way, so we can measure average performance as the cost over kind of lower bound, and we have the following result, right? So for different number of classes, we get a better ratio than the 2b minus 1 approximation. And for the b equal to 2 case, which is the kind of special case where we have a three approximation algorithm that's fully adaptive, we do comparably well. Okay. Cool. So let me quickly summarize. So we have non-adaptive constant factor approximation for the problem. We give a single list for probing that does not depend on cutoff values. We give 2 extensions for this problem, where we also obtain good results. And finally, if you open questions are the following. So can we get better constants? Maybe fully adaptive algorithms can help get kind of smaller constants. Can we deal with correlated setting over here? Because we do assume that items fail independently. And this kind of setting has been studied for a lot of stochastic optimization problems like stochastic knapsack, stochastic probing, stochastic matching, and so on. Can we think of more problems that fall under the same framework and can be kind of studied with this can be kind of studied in the same framework? Okay, thank you.
So do you know what happens if instead of having to determine the class exactly, you just need to determine it up to some confidence. So there's some parameter theta, and you need to determine the correct class to probability at least theta.
Yeah, we haven't considered that, but I suppose you could do that in the same framework. Like, you keep testing till you know that, given the probability of the stuff that remains, we can maybe say with high confidence that we'll be in a certain class or not. But we didn't consider that, and that would be kind of interesting extension to this problem as well. Yeah.
Thank you.
Do you know a lower bound on the gap between the adaptive and non-adaptive?
Actually,
is it?
No, it's
Small
not
constant,
known.
large constant.
It's not known. No. Yeah. Actually, there was some kind of recent work in the case when the weights are 1, and they have non-adaptive algorithms with constant like 5.8 and stuff as well. So I feel like maybe without weights, you should get low enough constants. And it's not even known if this problem is hard.
So let's thank the speaker.